That's where it died yesterday. Okay. But we're back. Okay, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today?
Pretty good.
Good to hear. All right, we're back. I bought a new Apple Pencil from Best Buy, or at least the Best Buy brand. So hopefully this will at least take us until the end of the semester. This one was more expensive than my previous one. My previous pencil was like a off-brand Chinese Temu, Apple Pencil for $10. So this was 40. So hopefully it shouldn't last 4 times as long, right? And so my previous one lasted 5 years. So this should take me until almost when I retire, maybe, for 20 years. Okay, so just like I mentioned on Tuesday, so I know the second half of last Tuesday was kind of scuffed because of the Apple Pencil. So I do want to go over a lot of the stuff that we went over last Tuesday, starting with the strong form. So we're going to start with the strong form for the 2D heat conduction problem, work our way through the weak form, and then get through the finite element form stuff today. Okay. So my hope today is that we can get through at least triangular elements. That is the element type for your final project, and so this is important for you to know. Okay. Technically, you can do the final project with the methods that we'll talk about today, or you can use the isoparametric method, which may be a little bit easier, which we'll cover after the midterm exam. Okay. And so another reminder on that, remember, our second midterm is going to be next Thursday. And so that is a week from today, April 23rd. So please make sure you're here for that. So same parameters, same resources that you had for the first exam. So there's a study guide posted online. I believe the homework solutions are all there for you guys to study for as well. You can bring a cheat sheet. So that's one 8.5 by 11 sheet of notes, both sides. You can bring that. You can write whatever you want. Except for the exam answers, but you would have to travel to the future because I've not written the exam yet. Anything goes for that cheat sheet. Okay. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. So let's start with the point that we kind of went over. Question. Yes, from the chat. Go ahead, Abdullah.
I'm audible.
Go ahead. Sorry.
I'm audible. My voice is clear.
It's a little bit soft, but I can hear you.
I have a question when I was saying the study guide, there is a thing like derivation. So does any derivation comes in the final exam?
I'm sorry. Let me try to raise the volume here. Let me see if that helps. Okay, go again. Sorry.
When I was following the study guide, there is a question regarding the derivation. So I have a question like, does derivation comes in the final exam?
You should be prepared for it. Yes.
Okay. So,
Okay.
and how many questions total there? Like five, or because I was following the midterm guides, like total four questions. Three is the theoretical, and the one is the one is the theoretical one, and three is the numerical one. The same one that they post midterm of 2024.
Yeah. So
Same.
it will have the same format as the sample exam that I posted. So there'll be 4 conceptual questions, 3 problem-solving questions, and so the problem-solving questions will involve the approximate solution to weak forms, finite element form solution in 1D, and also Gauss quadrature. Yeah.
Thank you so much.
All right. Sorry, Abdul. Did you have any more questions on the exam?
Oh, thank you so much.
Okay. Good. All right. Any other questions before we begin? Okay. All right. So let's go ahead and get started. Okay. So let's start with the topic that we kind of started kind of maybe halfway through the lecture on Tuesday, which is the strong form for the 2D heat conduction problem. Okay. All right. So now that we're in 2D, remember, we are working with a partial differential equation. Okay. And so our strong form has the following form. Okay. So we have K multiplied by partial squared T partial X squared plus partial squared T partial Y squared plus S of X and Y is equal to 0. Okay. right? Where our variable of interest here, or the variable that we are solving for, is T, which is the temperature field. Okay. Okay. Where T here is a function of X and Y, okay, because it is a two-dimensional solution. Okay. Another form for this equation here that we will use is that, we know that this term here, or this combination of terms, this is the Laplacian of the temperature field. Okay, where the Laplacian is given by nabla squared t. Okay, so remember that was a specific operator that we talked about. I think not last lecture, but the lecture before that. Okay. Where another way to express the Laplacian is the divergence of the gradient of the temperature field T. Okay. Okay, so that'll come into play later once we kind of work on the weak form. But I just want to say that here. Okay. Okay. And so another way to state the strong form for the problem is going to be K nabla squared T plus S of X and Y is equal to 0. Okay. Where K here, this is our thermal conductivity. Okay. S of X and Y here, this is our thermal generation. Okay. And of course, T that we defined above, that is our temperature field. Okay. Okay. So unlike the 1D problems, we can't solve for a solution to this problem without diving into partial differential equations. Okay, not that it's impossible. It's just kind of way beyond the scope of this class. And so the only way that we can solve this, or the only way that we'll be able to solve this for this class, is to actually just go straight into the finite element solution. Okay, and so that's kind of the plan for today. Okay, so for the 1D problems, we kind of took our time a little bit. We took a whole day to discuss strong forms and weak forms. We discussed, different ways to solve them. But for 2D problems, we're just, just as a function of time, just the amount of time we have left in the semester, we're just charging straight ahead to the finite element forms. Okay, but before we do that, we do have to define the form for the boundary conditions here. Okay. Okay. So just like in the one-dimensional problems that we've looked at, there are two types of boundary conditions that we can look at. Okay. So the first type are the Dirichlet boundary conditions. So Dirichlet boundary conditions have the same definition. So Dirichlet boundary conditions are going to directly specify the value of the solution at the boundary. Okay. Which in this case, since our solution is the temperature field, our Dirichlet boundary conditions are going to directly specify the value for the temperature at the boundary. Okay, so there's not too much to say with the Dirichlet boundary conditions. They do get a bit more complicated in 2D just because there's going to be multiple nodes or multiple locations where we're applying the Dirichlet, but more or less we're going to apply them in the same way. Okay. Now for the Neumann boundary conditions. Okay. So Neumann boundary conditions for heat transfer type problems like this take the form of a prescribed heat flux. Okay. Now, the mathematical form for the Neumann boundary conditions does change a bit because of the 2D. Okay. So for instance, right? So let's say we have kind of a two-dimensional domain like this, right? So I'm just using a square domain just as an example. Okay. And let's say that on this section of the boundary here, we have a prescribed heat flux. Okay? So the boundary condition that we're going to apply on that section of the boundary is going to be our Neumann boundary condition. This is our Q bar, prescribed heat flux. Okay. Okay. And so in order to apply this boundary condition, we need an equation, or we need a mathematical expression to relate the heat flux back to our temperature, right? Because essentially, our boundary condition should be constraining our temperature field to some extent. Okay. Okay, and so the mathematical expression, or the equation that we're going to use to do that, is an equation of heat transfer called Fourier's law. Okay. And so Fourier's law basically says that Q bar is equal to minus K multiplied by the gradient of the temperature field dot product with the normal vector. Okay. Now, the key kind of the keys to understanding this are kind of what lie inside the parentheses there. Okay. So on the one hand, we have the gradient of T. Okay. So if you remember gradient from our discussion about a week ago, gradient is essentially just the derivative of our temperature field in each given direction, right? So you have partial T, partial X, and partial T, partial Y, right? So since the temperature is a scalar field, when we take its gradient, we obtain a vector, right? So we have an X component of the vector, which is partial T, partial X, and a Y component of the vector, which is partial T, partial Y, okay? Okay. Next component of the boundary condition here is we have the normal vector n. Okay, so this is one of the biggest changes that you're going to see with two-dimensional problems is that, we now have to deal with directionality, right? And so in our one-dimensional cases, we only just had positive direction, negative direction, but now we can have X and Y direction, positive X, positive Y, negative Y, okay? That normal vector is a vector that points perpendicular to the surface where the boundary condition is applied, and it always points outward. Okay, so for instance, let me kind of zoom in here. So for this boundary here, the unit vector is going to be pointing in that direction there. So you can see that the unit vector is perpendicular to the surface, right? So it makes a 90-degree, and it points outwards. Okay. And so if you combine those two concepts, right? So you combine the fact that we're taking the gradient of the temperature and we're taking the dot product of that with the normal vector, right? Think about what the dot product represents. Okay? And so if you recall from vector algebra, right? When you take the dot product between two vectors, you're essentially computing the component that those two vectors share in common. Okay. And so whatever component of the gradient of t and whatever component of the normal vector, whatever they share in common, the dot product is going to, to express that. Okay. Now, if you take all this in its entirety, right? You take the gradient information, we take the fact that the normal vector points outwards from the domain, we take the dot product. All this is to say that when we compute the heat flux, we only care about the heat flux that's either leaving or entering our domain. Okay. right? So that's what our Neumann boundary condition is going to represent, right? And that physical interpretation, right? And so, you can say all this is just kind of physical explanation, right? We haven't gone any more into the math, but that I think that interpretation is really important because once we kind of get driving into the weak form, we're going to make this substitution into our weak form. And so I think having this physical understanding and interpretation of what the Neumann boundary condition represents is going to be important for it. Okay. Okay. Any questions on Neumann boundary conditions for 2D heat conduction? Yes.
Obviously, for the heat flux, is there a convention where negative is entering the system or?
Yes. Good ask. And so because the normal vector is pointing outwards like this, right? And so if the gradient of T, so let's say that, the heat flux, or let's say the gradient of T is kind of pointing in that direction as well, right? Right. So whatever we compute the gradient of the temperature field. So gradient of T and N are aligned together. So when you take their dot product, you end up with a positive number because they have components shared, right? But if you look at our expression here, right, we have a negative out in front of it, right? And so if you have heat that's leaving your domain, the convention for that is that you have a negative heat flux. And so, but if you have heat that's entering your domain, right? So let's say that, for this particular problem, right, we have the gradient of T going in the opposite direction, right? When you have two vectors that point in the opposite directions for each other and you take the dot product, you get a negative number, right? And so that negative number is going to cancel out with this negative number, you get a positive number. So if you have a heat flux that's entering your domain, that's going to be positive. Yeah. I like that convention. I know some people use another convention, but I think of heat leaving the domain as your system is losing energy, and so you should have a negative heat flux. Whereas if heat flux is coming in, your system is gaining energy, so you have positive heat flux. Yeah. Great question. All right, any other questions on Neumann boundary conditions? Okay, all right, so let's talk weak form now. We're just kind of speed running our way to the finite element form. Okay, so just like we did in the 1D problem, the process for deriving the weak form is exactly the same, okay? So to derive the weak form, we're going to multiply our strong form equation by a weighting function. Okay. Right, so the weighting function is going to play a similar role here, okay? And then we're going to integrate that across our entire domain. Okay. Okay. And just like in the one-dimensional case, our goal here is exactly the same. And so the reason we're going through this whole kind of process of weighting function and integrating is we want to soften, we want to lower the overall derivative order of the equation. Okay, so let's go ahead and do that. So let's write our strong form one more time. So our strong form is K nabla squared T. So I'm just using the shorthand, the vector form, plus S of X and Y is equal to 0. Okay. Okay. So let's go ahead and multiply. So, we have two terms here. And so we're going to multiply this first term by W of X and Y. That's our weighting function. Multiply by W, X, and Y. Should have given myself a bit more space there. Okay. And then we're going to integrate this on our entire domain, okay? But since we're in 2D, right, to integrate across a two-dimensional domain, we need a double integral. So integral, 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 integral. Okay. All right, so we have two different integrals here, right? So I've kind of already kind of split them up, okay? On the one hand, we have this integral on the thermal generation term. There's not much we can do with this term because, you know, we don't know the form of S here, okay? So this is our thermal generation integral, right? We're essentially going to leave it alone, right? Because the way that we evaluate this is going to depend on the form of S, which we've kind of left vague here, okay? Okay, so all we can do is just kind of just drag it along for the ride, right? I'm going to focus more on the first integral there because that one's the one that's more interesting. That's the one we're going to do integration by parts on. But we're not going to forget this one here. So we want to make sure that we bring this kind of along for the ride. Okay. Okay. Eventually, you know, when we put this into the finite element form, this thermal generation function is going to make a contribution to our element forcing vector. Okay. But that's just kind of way in the future. But I thought I would mention that here. Okay. So for that term, I'm not going to focus on that just because, you know, we can't really do anything mathematically with it. But just know that, you know, that one's going to be along for the ride. Okay. Okay. So let's focus on the other integral instead. Okay. And let me rewrite it down here just to make it a bit more clear. Okay. So we have integral of w of x and y, weighting function multiplied by k. And so the Laplacian, I'm actually going to break it up. And so I'm going to break it up into a divergence operation and a gradient operation. Okay. So it's multiplied by nabla dot product with nabla t. Okay. Integral with respect to area. Okay. Okay. So we want to work on this integral here because, you know, we have basically a situation where we have unbalanced derivatives, right? And so this term, right, even though it's in slightly different form because of the vector nature, right? This term here has a second order derivative. Okay. So we want to address that. We want to lower that order of derivative because our weighting function, okay, this weighting function has no derivative. Okay. Right. And so we're going to basically apply integration by parts in 2D. Okay. And so we're going to use Green's formula for this. And so by applying Green's formula, we can then perform integration by parts in 2D. That's going to balance the derivatives. Okay. We're also going to get another byproduct term from this. And so we're going to get a term where we're going to evaluate our Neumann boundary condition. But that's essentially what we're going to do. Okay. Okay. All right. So we apply Green's theorem. And so we say that this integral here, we're going to split it up into two, right? And so on the one hand, we have our term with our balanced derivatives. Okay. So after applying Green's formula, we end up with this here. Okay, so we have a minus double integral of the gradient of w multiplied by k multiplied by the gradient of t. Okay, dA. Right. So we essentially move that first divergence operation, the first nabla, we've essentially shifted that onto the W, okay, using integration by parts. Right? But that also creates another byproduct term, which is the Neumann boundary condition. Okay, and so to this we're going to add. Okay. This right here is going to be a line integral around the boundary, right? So this is an expression here that's only evaluated on the boundary of our domain, okay, of W of x and y multiplied by k multiplied by gradient of t dot product with n ds. Okay. Okay. And so let's kind of debrief here a little bit. So first thing we obtain after applying Green's formula is we get a double integral with a balanced derivative. Okay. And the second expression that we get here is a line integral that goes around the boundary of our domain. With the operative word there being boundary, okay? Hence, we're going to apply boundary conditions there. Okay. All right, so we're almost there. So, that was kind of the big step, applying our integration by parts, okay? Now, another thing that we're going to do here before we kind of combine this together, we have this expression here, the k times the gradient of t dot product with n, okay? That should look familiar because that right there is the expression for our heat flux Neumann boundary condition. So that right there is our expression for Q hat or Q bar. Okay, good. All right, so now that we've done the integration by parts, we've substituted for a Neumann boundary condition. Let's put it all together to express our weak form. Okay. So if we combine this with our thermal generation term, okay, we end up with the following expression. Okay, so first we have our balanced derivative term, our balanced derivative term here. So we have a minus double integral gradient of w multiplied by k multiplied by the gradient of t dA, okay, plus our line integral Neumann boundary condition term. And so, one subtle thing, I should have mentioned this up here, right? So this term here is a positive k gradient of t dot product with n. If you go back up to our Fourier formula here, or Fourier law, right? Going back to the question that was asked earlier about the direction, remember there's a negative that comes out in front here. So we need to make sure we account for that negative down here as well, okay? So we plug in for that, we actually get a minus line integral around the boundary, w of x and y times k times q bar. Oh, sorry, the q bar takes the place of k as well. W q bar ds, okay, plus our thermal generation terms. We have a double integral w of x and y, s of x and y, dA, okay, and all this is equal to 0. Okay. Okay. So one last small thing before we present this as the weak form, right? That's going to be convenient for us when we do finite element forms, is we're going to take this first integral here with the balanced derivatives, okay? And we're going to actually move it to the other side of the equation. So we're going to add it to both sides, and you'll see why kind of very soon. Okay, so after we do that, we end up with the following expression, and I'm going to flip it as well, right? And so I'm going to basically have the balanced derivative terms on the left-hand side with a positive sign, and everything else on the on the right-hand side. Okay, and so we do that, we get double integral gradient of w times k times gradient of t dA is equal to minus line integral around the boundary w of x and y dot q bar ds plus double integral of w of x and y s of x and y dA. Okay, so this entire expression here, this is the weak form of our 2D heat conduction problem. All right, any questions on this expression here? Okay, good. All right, so a couple more points before we move on to the finite element form. Okay. So I should have mentioned this earlier, but our weighting function here has the same requirements as our weighting function from 1D. Okay. So same as 1D. So one of the major requirements on the weighting function is that at the locations where our Dirichlet boundary conditions are applied, our weighting function is required to have a value of 0. Okay. So wherever we have a prescribed temperature, we're going to require our weighting function equals 0 at those locations. Okay. Okay. Another thing to note here is that by balancing the derivatives, right? So now the highest order derivative that we have here is first order. Okay. And so we get the exact same benefit that we get for 1D, is that this allows us to use linear shape functions. Okay. Right, and so that's what we're going to focus on, right? So not that quadratic shape functions are bad in any way. They're just kind of too much of a hassle for us to handle in this class. Okay. And one last point before we move on. The reason I kind of arranged the formula in this way is that eventually you're going to see that everything on the left hand side of the equal sign, that's going to comprise our element stiffness matrix. Okay. So the left hand side of the weak form, this is going to form the basis for element stiffness matrix. Okay. And the right hand side, This is going to form the basis for our element forcing vector. And so if you compare this to our equation for one-dimensional finite elements, those exact terms are going to match up as well, okay? And so for our 1D finite elements, we had our term on the left-hand side for that had our balanced derivative. That comprised our element stiffness matrix. And on the right-hand side, our element forcing vector was comprised of the Neumann boundary condition together with any kind of body force or any kind of thermal generation term, okay? So this term here is literally just a two-dimensional version of our 1D finite elements. Okay. Okay. So with all that stated there, so now that we've kind of gone through the weak form, we are now ready for the finite element form for these equations. Okay. And at that point, we'll have essentially caught up to what we covered on Tuesday. So this is all just recap of the stuff that I went over just by zooming in, zooming out on the Dropbox notes, which I know was a terrible experience. So hopefully this was a bit better for that. Okay. Any questions on any of this? Okay. All right. So let's go ahead and jump into the finite element form. Okay. So just like our one-dimensional problem, our weak form here is going to form the basis for our finite element form, okay? But there's going to be one important change, right? So currently our weak form, requires us to integrate our equations across our entire domain. Okay? Right? So that's how we did our 1D problems as well. So when we solve for our approximate weak form solutions, remember we are integrating across the entire domain from x is equal to 0 up until x is equal to l, right? In 2D, this becomes a lot more complicated because our domains can take any number of shapes, okay? So it's not really practical to perform this integration across the entire domain when our domain can take any kind of complex shape. Okay. All right, and so the solution to this is to basically break up our domain, right? And so in other words, we're going to apply a mesh to our domain to break up our domain into lots of tiny, tiny elements, okay? Okay. And hopefully the idea is that all of those elements have the exact same shape, right? So they're either going to be triangles or rectangles, okay? Then for each element, we can consider each element to be its own little miniature domain, right? And so we're going to apply our weak form to each of those elements. Okay. So instead of doing one weak form for the entire domain, We're going to do many, many, many weak forms for each individual element, okay? And then to ensure that our solution is nice and smooth and continuous across element boundaries, we need to enforce continuity between different elements, right? And so that means our solution must be nice and smooth and continuous, no jumps or discontinuities going from element to element. Okay. Okay. So let's kind of illustrate that whole process here. Okay. So let's say we have our domain here. Okay. So this is our solution domain. Right. So our solution domain is this kind of weird oblong looking potato looking thing. So we can't apply the weak form directly to this because the domain is so weirdly shaped. Okay. Instead, we're going to mesh. Okay. We're going to take our potato shaped domain. We're going to apply a grid to it. I guess now it looks like a planter's peanut, I guess. But the good news is that with this domain, I don't know why Microsoft is doing this right now. Cancel. Okay. So with this domain here, right? All of these elements here have a nice kind of uniform shape, right? So let's apply the weak form to each element. Okay. Not just that element in particular, but for every single element. Okay. Because the good news is that for if we mesh, properly, each of those elements will have a nicer shape. It's going to be a lot easier to perform the integration. Okay. But then to make sure that we're actually solving our solution, right? We're going to enforce rules of continuity so that when you go from one element to the next, right? Our solution is nice and smooth and satisfies all of our conditions for continuity. Okay? Okay, so that's kind of the approach, right? So our weak form is not changing, but just how we apply it is going to change as well. Okay. All right, and then eventually, we're going to get to a stage where we're going to have shape functions that define our element, and then we're going to define our element stiffness matrix in terms of those shape functions. But all of that is kind of due in good time. Okay. All right, so our approach is no different, right? So this approach that I've kind of outlined here, this is the exact same approach that we did in 1D, right? Obviously now our equations are more complicated because we're in 2D, right? But the biggest difference is that now our elements are going to have much more complex shapes as well. Okay? Not really complex. There's nothing really complex about a triangle. Okay. Now we have different options. Okay. And so the two options that we'll be discussing in this class is that we have the 3-node triangle. Okay. And then we have the 4-node rectangle. Okay, so we'll go through both of them and kind of see what those look like. And so we're basically going to, for each of the shapes here, we're going to, first of all, derive what their shape functions look like, apply them to our weak form, and then we will get expressions for the element stiffness matrix and the element forcing vector for those types of shapes. Okay. Now, I will warn you that, because the matrices get fairly large here, and these are fairly complicated expressions for the shape functions, there's limitations in terms of what we can do by hand. And so, I'll do my best to kind of illustrate the concepts for you as much as I can, but, we're not going to do traditional kind of example problems here. Okay. That's why, the second midterm it's positioned where it is in the class. Because, after the second midterm, everything we do from here really is just in preparation for your project and for the code. So these calculations, these algorithms, really you can't, it's just not practical to do these by hand, but it's still important to know the process, to know the steps so that you can implement in the code for your final project. Okay. Any questions on this here? Okay. All right. So let's start with the triangle. That one's the always the first 2D element to do. Okay. So let's look at the 3-node triangle. Okay. All right. All right. So we're just going to draw a triangle here. Okay. Okay. So we can label all the nodes here. So this is node 1, node 2, node 3. Okay. Doesn't really matter which node is which. We kind of just do an arbitrary triangle here, but someone has to be 1, someone has to be 2, someone has to be 3. Okay. We are going to label these, or we're going to specify the physical locations of each node. So that means we're going to know its x and y coordinates. So x1, y1, x2, y2, x3, y3. Okay. Right. And also, right, to ensure that we have solution continuity, we're going to define the values for the solutions at each of these nodes as well. Okay. So we have T1, the temperature solution at node 1. We have T2, which is the temperature solution at node 2, and T3, the temperature solution at node 3. Okay. Okay. Good. All right. So the first step here, and the first step to any kind of finite element analysis, is that we need to assume a functional form for the solution. Okay. Right. So this is where our approximation comes into play. Right. So remember, we want to assume a linear shape function. Okay. So that means our assumed functional form is also going to be linear, right? But also keep in mind that we have multiple dimensions now. So we have not only x, but y as well, okay? All right, and so our assumed solution here, TE of x and y is equal to A0 plus A1 times x plus A2 times y. So you have 3 terms here, which matches the number of nodes that we have in our element, right? So a 3-node triangle will have 3 terms to its assumed functional form. Okay. Right, and so you can see pretty clearly here that this function is very clearly linear in x and y. Right, so we have a separate function for x, and a separate term for x, separate term for y, and we have our constant term. Okay. Okay. So first thing we're going to do is we need to solve for the values for these coefficients, right? So A0, A1, A2, these are unknown coefficients. Okay. Right. And so the way that we're going to solve for them, right? Same way that we did in 1D to enforce solution continuity, we're going to enforce that the nodal solutions are satisfied by our assumed solution. Okay, so we have three nodes here with three solution values and three coordinates. And so that's going to give us three separate linear equations. Okay. Okay, so equation one, we have our assumed function evaluated at x1 and y1. Okay, this is a0 plus a1 x1 plus a2 y1, right? And that, of course, is going to be equal to t1, which is the value of the solution at node 1. Okay. Okay. Next, we have the value for our solution field evaluated at x2, y2. So this is a0 plus a1 x2 plus a2 y2 is equal to t2. Okay. All right, and then finally we have the solution at the third node. This is TE x3 y3 is equal to a0 plus a1 x3 plus a2 y3 is equal to t3. Okay, so we have our three equations, right? And so we can use them to solve for our three unknowns, a0, a1, a2, okay? Right? So this is you know, not the worst 3x3 system to solve, but it is all symbols. And so that does make things a bit more challenging. Okay. So just like I usually do, we're going to say that, we're going to magically obtain the solution. And by magically obtain the solution, that means that, I worked this out in 2020 when I first taught this class, and I'm just going to write this solution here again. Okay. Right. So after solving for our unknown coefficients, okay, we can then put our solution in a form that involves our shape function, right? Because essentially that's what we want to do. Okay. So we can have TE of x and y is equal to T1 and 1 of x and y plus T2 and 2 of x and y plus T3 and 3 of x and y. Okay. So we want to put things in terms of our shape functions just to make things a little bit easier for us when we compute our elements difference matrices. Okay. Okay. And so if you want a refresher on this, we kind of worked this out in detail for the 1D equations. So after we solve for A0, A1, A2, there is a little bit of algebraic manipulation in order to get this expression here. Okay. So if you want to work it out yourself, the way that we do that is by after plugging in and solving for A0, A1, A2, okay. Essentially, you need to basically group like terms according to the nodal solution. Okay, so we're gonna have one term with T1, another term with T2, another term with T3. Okay, and everything that's multiplied by T1, T2, and T3, those form our shape functions here. Okay. Okay. So I will give you their exact expressions. Okay. So N1 of x and y for a three-node triangle, right, is equal to 1 divided by 2 times a, where a here is the area of the triangle. Okay. Multiplied by x2, y3 minus x3, y2 plus y2 minus y3 multiplied by x plus x3 minus x2 multiplied by y. Okay. So that's n1. Let's write out n2. Okay. Second shape function is 1 over 2 times a multiplied by x3, y1 minus x1, y3 plus y3 minus y1 multiplied by x plus x1 minus x3 multiplied by y. All right, and then finally we have n3. N3 is the third shape function, so this is 1 over 2a multiplied by x1, y2 minus x2, y1 plus y1 minus y2 multiplied by x plus x2 minus x1 times y. Okay. Okay. So it is a little bit messy, right? So there's kind of a lot going on here, but hopefully you can see the structure, right? And so each of these shape functions, they have the exact same functional form as our assumed solution, right? And so each of these will have a constant term, right? So, for the first equation there, we have x2, y3 minus x3, y2. That's our constant term. We have a term here that's multiplied by x, and another term that's linear in y, okay? It only just gets complicated just because of all the different coordinates, right? But these are, these are kind of what we have. Okay. Okay. All right. Any questions on the shape functions for a triangular element here? Okay, good. All right, one other thing that we'll do, just because we're going to need them when we compute the element stiffness matrices, let's compute the shape function derivatives, okay? So we're kind of doing this preemptively, but I think just having them all laid out will make things easier for us when we actually do our calculations. Okay? Okay, so let's compute our shape function derivatives. Okay. Now this gets a bit more messy because we have 3 shape functions, and so that's up from 2, but our shape functions are also functions of x and y, and we're going to take derivatives of both of them. And so there's going to be 6 total shape function derivatives, right? X and y derivative of each of the 3 shape functions. Okay, so first we have partial n1 partial x. This is equal to y2 minus y3 all divided by 2a. Okay. We also have partial n1 partial y is equal to x3 minus x2 divided by 2a. Okay. Next, we have partial n2 partial x is equal to y3 minus y1 divided by 2a. And then partial n2 partial y is equal to x1 minus x3 divided by 2a. Okay. And then partial n3 partial x is equal to y1 minus y2 all divided by 2a. Partial n3 partial y is equal to x2 minus x1 divided by 2a. All right. Quite the doozy. It's a lot, right? So, this kind of reminds me a little bit of our direct stiffness method, right? And so it's for these kind of 2D problems, it's very easy to get lost in the details of everything that's going on. And so, and that's very easy for me to say just because I'm up here, the one talking, but you guys are the ones that's kind of furiously trying to keep up and write things down, right? And so, yes, it is important to write everything down and to kind of, get all these details. But I don't want you guys to lose sight of kind of the overall kind of objective and overall kind of steps that we're doing, because ultimately that's going to be what's more important, right? So the details will come, right? So when you're writing your code, the details will kind of come as you're writing the code. But I think what's going to be more helpful for you guys when you're doing your final project is to have a better, or is to have kind of a more broad, kind of high level understanding of kind of what the purpose of each step does and which step leads to the next step, right? I think that's going to be more valuable for you than just trying to memorize all the details themselves. Okay, so write down all the details. Don't try to really memorize them. Just kind of keep the overall kind of steps in mind. That's what's going to help you the most. Okay. Okay. All right. So now that we have our shape functions, now that we have our approximation function here, okay, we are now ready to start moving this into our weak form. Okay. 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 So let's go ahead and start moving this into our weak form. Okay. So we have basically everything that we need, with a little bit more processing, but I think it's about ready for us to do this. Okay. So let's start with the left-hand side. We'll leave the right-hand side alone. We'll probably do that next week, next Tuesday. Okay. And so the left-hand side of our weak form was the following. So we had double integral of the gradient of our weighting function multiplied by k, multiplied by the gradient of t, dA. Okay. So we want to plug in, right? So k is k. So k we don't have to worry about. K is usually just a constant. Okay. But we do want to plug in for these two quantities here, right? And so we want to plug in for W and we want to plug in for T to put these expressions essentially in terms of the shape functions. Okay. Okay, so let's compute our gradients then, just because we know that we need them, right? So we have our t function. Okay, so t of x and y is equal to t1 and 1 of x and y plus t2 and 2 of x and y plus t3 and 3 of x and y. Okay. Similarly, our weighting function is going to have the same form, right? So remember that was kind of the assumption that we made, was that our weighting function utilizes the same shape function as our solution, but with different coefficients. Okay. So our weighting function here is going to be W1 and 1 of x and y plus W2 and 2 of x and y plus W3 and 3 of x and y. Okay. All right, but we don't want the temperature and we don't want the weighting function by themselves. We want their gradients. Okay. So let's compute the gradients based on these expressions for t and w. Okay. Okay, so let's start with the gradient of t. Okay. Okay. Remember, gradient will take our scalar function and turn it into a vector. So we're going to have one component that has the x derivative, one component that has the y derivative. Okay. All right, so we have partial t, partial x, right? That's going to be one component of the vector. The other component is going to be partial t, partial y. Okay. Okay, so we're going to take x derivative and y derivative of t of x and y that we have above. Okay, so that's going to be t1 partial n1 partial x plus t2 partial n2 partial x plus t3 partial n3 partial x. Okay, that's the first component of the vector. Second component is going to be everything, but we're going to take y derivatives of our shape functions. So t1 partial n1 partial y plus t2 partial n2 partial y plus t3 partial n3 partial y. Okay. Right, so this is kind of a big change from our 1D, right? And so our gradients are now vectors, and so we need to compute each component of the vector. For each component, we're taking the derivative with respect to a different variable, okay? Okay, I'm going to do one more step here just to make things a little bit simpler for us, right? So even though this is a vector, right, we know that both components of the vector have these coefficients, right? T1, T2, T3, okay? So what we can do is we can factor them out into its own vector. Okay. Right, and then that's going to make things a little bit easier for us when we plug in if it needs. Okay. Okay. And so if we factor them out, we kind of take these and we kind of pull them out to the right, right? We get the following kind of multiplication between two vectors. Okay? And so on the one hand, we have a 2 by 1 vector here. I don't know why I drew that parenthesis so weird. Okay. We have partial n1, partial x, partial n2, partial x, partial n3, partial x. Okay, so that's the first row. So that contains all of the partial derivatives in that first row there. Okay, then we have the y derivative. So partial n1 partial y, partial n2 partial y, partial n3 partial y. Okay. Okay. So we've essentially created a 2 by 3 matrix here. Okay. So we have 2 rows and 3 columns, and then we're going to multiply that by a column vector, okay, that contains our nodal temperature. So T1, T2, T3. Okay. And so this column vector here is going to be a 3 by 1 vector. Okay. All right, so this step seems a bit strange, but you're going to see that it's going to help us form our element stiffness matrix a lot better. Okay, and you can check the math. So you can check the linear, you can check the matrix multiplication here, and you can see that we still end up with the same thing as above. Okay, because if you multiply these inner dimensions, right? So remember the rule for multiplying matrices together is that you can do that if their inner dimensions agree, right? And so our inner dimension is 3 and 3. Right? So that means we can do this matrix vector multiplication, right? And if you do that, you multiply the first row by this column, second row by the column vector, we end up with this guy back up here. Okay, so all we did was we just factored out the temperature coefficients. Okay. Okay. And then by that same token, we can do the exact same exercise for the gradient of W. Okay. So I'm not going to write out all the steps for the gradient of W again. They're all exactly the same. So there's, you're going to get a vector, right? Partial W, partial X, partial W, partial Y, all with the same coefficients, okay? And we can do the same thing where we factor out the W coefficients away from the shape function derivatives, okay? So that's kind of what this is all about, is to kind of isolate a matrix that just has the shape function derivatives and separate them out from the coefficients of the expression. Okay. Okay, and so we do that. We get the following. So we have gradient of W is equal to row vector W1, W2, W3. Okay. This right here is a 1/3 vector. Okay. And then we're going to multiply that by a 3/2 matrix. Okay. A 3/2 matrix that contains the shape function derivatives. Okay. And so this can be partial n1, partial x, partial n2, partial x, partial n3, partial x. Okay. Then partial n1, partial y, partial n2, partial y, partial n3, partial. Okay. All right, so we can check the dimensions here again. And so we have an inner dimension of 3, inner dimension of 3. So the matrix vector multiplication works out in this case. Okay, and then we get the same result as above. You're probably wondering, right? So if you look at these two expressions for the gradient of t and the gradient of w, right, we've kind of swapped them, right? So for the gradient of t, we have the t coefficients on the right, and for the w vector, we have the w coefficients on the left. Okay. So they're both equivalent, right? So we can easily just kind of do the switcheroo and get the same thing as well. But we do it this way, right? The reason we do it this way is that if you look at our weak form, right? I'll come back to that. I know some of you guys are still writing this down. Okay. If you look at our weak form, our gradient of w is on the left-hand side, and our gradient of t is on the right. Okay. And so if we plug in for these expressions the way that they are, right, we're going to get our we're basically going to get all of our coefficients on the outsides of our expression. Okay. So we're going to have W1, W2, W3 on outside on the left. Okay. And then for gradient of t, since that's on the right, if we plug in the expression below, our column vector T1, T2, T3, okay, this is our coefficient vector. It's going to be on the outside on the right. Okay. So that's just, it's just, we're just doing it that way just to make our multiplication just a lot easier. Because if those coefficients were in the middle, then it just kind of makes things just a little bit messier. Okay. So that's why we have these kind of two different expressions, even though they're very similar, right? They both represent a gradient, but we have the coefficients on the left for one of them, the coefficients on the right for the other one. Okay. Okay. All right, so let's plug this in, and then we will write out our element stiffness matrix, and then we will call it for the week. Okay. Okay, so we're going to plug these into the weak form. Okay. So our weak form, I'll write it again down here, is double integral gradient of W multiplied by K multiplied gradient of the temperature field dA. Okay. Right. So we're going to plug in our two expressions for the gradient, keeping note of the consideration I just said, where we want the coefficients on the outside. Okay. Because these coefficients, they're constant, so they're not going to take part in the integral at all. Okay. So we plug in for gradient of W. We end up with W1, W2, W3 on the outside of the integral here. Okay. All right. Multiplied by our 3/2 matrix, partial n1, partial x, partial n1, partial y, partial n2, partial x, partial n2, partial y, partial n3, partial x, partial n3, partial y. Okay. Multiplied by k. Okay. Then we have our shape function matrix from our temperature gradient. So we have the exact same one. So partial n1, partial x, partial n2, partial x, partial n3, partial x, and all the y derivatives as well. Okay. dA. And then on the right-hand side here, we have our temperature coefficients. So T1, T2, T3. Okay. And those are constant, so they do not take part in the integral at all. Okay. Okay. So we are out of time, unfortunately, but so we will pick this up on Tuesday when we come back. Okay. And so what we're going to do on Tuesday is that we're going to finish up this matrix multiplication. We'll carry out the integration, and we'll plug in for the shape function derivatives, and this will give us our expression for the element stiffness matrix for a 3-node triangle. Okay. So everything in these red square brackets, this is our element stiffness matrix. Okay. All right, and so, you can see in this case, the devil is in the details. And so, these are just the shape function derivatives, but we computed the shape function derivatives. And so it's going to be a lot of kind of plugging in and kind of getting all that stuff in. Okay. One small thing you can pick up here is you can look at the size for elements matrix, right? So if you perform that matrix vector multiplication, or I guess matrix multiplication, you can see on the interior here, we're going to end up with a 3x3 matrix. Okay. Which, all things considered, considering all the other problems we've seen in this class, a 3x3 is not bad, right? That's only 9 expressions in total. There's just a lot of multiplication and a lot of shape functions that go into that 3x3 matrix. And so, again, we're not really going to be computing these by hand, but we are going to write code to do this for us. Okay. All right. So thank you guys for coming today. I hope you guys have a good rest of your day. Hope you guys have a good weekend, and I will see you guys on Tuesday.
You have to buy new pen.
I did. Yeah, I was telling people before the $10 Temu Apple Pencil I had for 5 years, it finally broke. So I went to Best Buy yesterday, got the $40 Best Buy brand.
Yeah. Well, you got a good ROI on $10.
Yeah, I was gonna say this. So this was 4 times expensive, so it shouldn't last 4 times as long. So I should use this until I retire. That's my hope. Oh, sure. Yeah, I can look really quick.
If I have to, I'll come on.
You know what? Actually, because I think the next lecture's coming in, I'll see. But if we don't have time, you can always just email it to me.
Yes, okay.
Because I didn't have too much time to finish that, and then there was the second code for the homework too.
Yeah.
When I looked last, there was 2.
Okay. So 541.
Yeah.
I think
which
it's
one?
called a homework frame.
Okay.
So that one's the one that.
Yeah.
It's been like that for a while.
Oh, so this is back from the frame code.
Yeah.
Got it.
Fall
Okay.
terms?
Yeah.
They just like slowly open.
You know what? Actually, go ahead. Let's do email. So go ahead and email me, and then I can take a better look at that time too, and then I'll give feedback.
Yeah.
So you just send it tonight, and then I'll try to get back to you tomorrow.
Okay.
Yeah. Yep.
Yeah.
So let's
Oh, okay. I haven't went. I had Dr. Wait for.
Oh, so there was also another code for the truss.
yes.